This ship is right now drifting in the middle of the Pacific Ocean. To get from the US to China, it needs to go about 15 to 20 days without stopping. And the whole time it's running not on gasoline, not on diesel, but on this. The fuel looks nothing like what you pour into your car. Imagine asphalt. Yes, regular asphalt, but at the stage when they're just starting to lay it down. That thick, black, sticky mass. And the crazy part is that this exact stuff is what pushes giant ships across the oceans. The mass is so thick you can't simply pour it into a tank, you have to heat it up. Otherwise it'll just solidify like cold grease in a frying pan. And while we're talking here, about 50 to 60,000 cargo ships are making their way across the oceans. Almost every one of them is moving thanks to that black goo. Container ships, tankers, bulkers, global trade exists because this asphalt exists. But what is this substance anyway? Let's figure it out. Asphalt energy. An unobtrusive reminder to do that thing under the video. So what kind of fuel is this anyway? Turns out it goes by a whole bunch of names. In shipping, they really love confusing regular people. The same product can go by 3 different names, and everyone will still insist they're talking about something different. Heavy fuel oil is a perfect example. Basically, it's just plain old fuel oil, the same black stuff they burn inside a ship's engine so the whole thing can actually move. They pour it into the massive engines of container ships, into bulk carriers hauling ore and coal, into cruise liners, and even into oil tankers. Yes, a tanker can carry crude oil, but it sails on fuel oil that's denser and heavier than that very crude oil. And there's a whole pile of other names too. Number 6 fuel, bunker C, very low sulfur fuel oil. They're all just variations of the same black substance. The name changes, but the essence is the same. It's oil the ship brings along to feed its own engine. When this thick mass burns in the combustion chamber, it releases energy that the engine converts into the spinning of the propeller or into powering the generators. In short, this whole giant machine moves forward simply because there's black goo burning inside it. The production of this black goo starts back at the refinery. When crude oil goes through its cleanup stages, all the light fractions are pulled out first, the very parts used to make gasoline, kerosene, and other familiar fuels, and what's left at the very end is a thick sludge-like residue. In terms of texture, it's basically like peanut butter, only black and toxic. It's packed with nasty stuff, and this very substance becomes the base for marine fuel. But in this state, the stuff is completely unusable. It has to be diluted with lighter fuels like regular diesel or marine gas oil just so it can float and not turn into a brick. These blends are what create different kinds of heavy fuel oil. As I mentioned, the marine industry uses different names for these blends. If they're mixed with lighter fuels, you get what's known as an intermediate fuel oil, also called IFO. They're classified by viscosity, basically how thick the mixture is. And if the blend contains more of that heavy black residue than light fuel, the mixture automatically falls into the heavy fuel oil category. Heavy fuel oil feels almost like glue, thick, sticky, stretchy, and incredibly hard to move through pipes. So hard, in fact, that at a normal temperature of about 68 degrees Fahrenheit, you can't pump it properly at all. That's why ships heat this goo in advance. To make it even slightly fluid, they have to warm it up to at least 104 degrees Fahrenheit. And at 59 degrees Fahrenheit, it's basically like bitumen, the road mix they use to pave highways. And now imagine this, the heating system fails, the crew is stuck, the fuel becomes so dense that you can't pull it from the bunker into the settling tank, it just won't move. And if the fuel is low grade on top of that, you get a second circle of hell, it clogs the filters. The crew has to clean them constantly because the viscosity goes up, the system load goes up, and the whole job turns into an endless, filthy marathon. And when you store such huge volumes of heavy fuel on board, a dense sludge slowly builds up on the bottom of the tanks, a thick layer of waste left after the heaviest particles settle. When we were making this video, I stumbled on a bunch of clips where people confidently say that this kind of fuel gets loaded into ships with shovels. Well, that's just not true. If you're not familiar with the shipping world, the word bunkering probably sounds odd, but it's simply the process of fueling a ship. Not some tiny car tank situation, but a massive system that keeps the whole vessel running. Modern ships need a lot of fuel. It powers the main engine, the auxiliary engines, the boilers, everything that keeps the ship alive on its voyage. And if the fuel runs out, or if it's poor quality, the vessel just stops. So yeah, bunkering is a crucial part of marine logistics. Here's an important distinction. When a tanker loads crude oil, that's cargo. But bunkering means taking on fuel for the ship itself. The refueling can happen at the pier, at anchor, with special bunker barges, or even at dedicated terminals. It depends on port regulations and the local infrastructure. First, they prepare the ship, the tanks are cleaned, checked for debris or water, then a bunker barge or a small tanker comes alongside. Through thick hoses and fittings, the fuel is pumped directly into the tanks. During the whole operation, the fuel is constantly monitored. They check its quality, temperature, and purity. But there's another key thing. You can't just take heavy fuel oil and feed it straight into the engine. Like I mentioned, it's too thick, so ships have an entire system to prepare it before burning. First, the fuel is stored in a tank where it's heated with steam. There are special coils inside. They usually keep it at around 104 degrees Fahrenheit so it can at least flow. Then it's pumped into a settling tank and heated further, up to the temperature where it can go into the separators. After separation, the fuel reaches the service tank already heated above 176 degrees Fahrenheit. Only at that point does it get thin enough for the engine to burn. So what's with the shovels then? Basically, loading heavy marine fuel oil with shovels is impossible. And honestly, probably illegal too. It's a thick, sticky liquid that you can only move through hoses and pumps. To make it flow at all, you have to heat it and run it through filters. All the official procedures involve pumps, heaters, separators, meters. No shovel-wielding humans. People in the comments under those clips were right. If that fuel were really loaded by hand, it'd take ages. And that's true. A pump moves fuel faster than a person can even swing a shovel once. Physically, it just wouldn't work. So where do shovel videos come from? They do exist, but usually it's something small, fuel for a small generator, a fishing boat, or some random local job. Definitely not for a big cargo vessel. It's interesting, by the way, that this fuel doesn't just look unusual, it's also incredibly harmful. I mean, it's toxic on its own, but in water and under sunlight, it gets even worse. Like, significantly worse. Exposure to heavy fuel oil is dangerous for both people and wildlife. It contaminates the environment in multiple ways at once. And yeah, the news usually talks about the war on carbon. The shipping industry likes to point out that its share is only about 3% of global carbon emissions, so supposedly it should be excluded from the Paris Agreement. They claim the emissions are hard to estimate across countries and shipping is too important for global trade anyway. But the problem is that it's not just about carbon. Heavy fuel oil contains a massive amount of sulfur, about 35,000 parts per million. That's insanely high. Because of that, roughly 8% of global sulfur dioxide emissions come from shipping alone. When this gas mixes with water, it turns into an acidic blend. That's where acid rain, corrosion, and respiratory illnesses come from. Plus, there are nitrogen oxides, pollutants that pollute the air and literally attack your lungs. At the start of the coronavirus pandemic, scientists noticed an interesting connection. In regions with high nitrogen oxide levels, people got sicker, simply because their airways were already weakened by constant pollution. And the heavy particulate matter from nitrogen oxides can trigger serious lung diseases, especially in children. Estimates say particulate emissions from shipping cause about 400,000 premature deaths per year and lead to more than $50 billion in healthcare costs. And even that isn't the full story. Scientists are only now starting to study how dangerous heavy fuel oils truly are. They contain a lot of polycyclic aromatic hydrocarbons, or PAHs for short. These are chemical compounds linked to cancer risks, but the scariest part is something else. Under ultraviolet light, basically regular sunlight, heavy fuel oil becomes even more toxic. These substances can be absorbed by organisms and sharply increase their mortality. In extreme cases, UV light makes them so aggressive that shells and coral start dissolving within minutes. So why is this fuel still so common if it's so harmful? The answer is as simple as it gets. It's cheap. Even radically cheap by global standards. In the early 19th century, cargo ships were powered by sails and moved wherever the wind pushed them. Then steamships arrived and the world gradually switched to engines. The first marine engine that could run on heavy fuel appeared in the 1930s, and that's when the tech race began. Companies poured money into R&D, engines got bigger, stronger, more efficient. And starting from the 1960s, heavy fuel oil became the undisputed king of shipping. Thick, dirty, toxic, but incredibly cheap and easy to get. International trade grew on it, and today it accounts for more than 90% of all global cargo transport. Without exaggeration, this stuff is the backbone of the entire maritime industry. Why the 1960s specifically? That's when oil refining made a leap forward. Refineries learned to squeeze more valuable fractions out of crude and sell them for more, while the leftover, that black goo, was repurposed as cheap fuel for the fleet. And that's how it all started. Today, about 60% of large ocean-going vessels, roughly 60,000 ships worldwide, run on heavy fuel oil. Cargo ships, cruise liners, ferries, tankers, bulkers, all these giants move thanks to cheap fuel oil. The main reason for its popularity hasn't changed: the price. Heavy fuel oil costs about 30% less than cleaner alternatives. Critics say that low prices largely depend on loose environmental standards. The International Maritime Organization, based in London, sets the rules for emissions at sea, and the limits for sulfur dioxide and nitrogen dioxide in heavy fuel oil stayed understated for a long time, not least because of pressure from the shipping industry. Long story short, cheap fuel became a habit, and many experts believe that this very habit is why the maritime sector kept putting off investments in cleaner tech for years. And if there's an oil spill, this specific fuel is the absolute worst to deal with. It's thick, sticky, and clings to everything. Because of that, it's almost impossible to collect quickly, and the pollution can linger for years, especially in places where birds live. Getting rid of heavy fuel oil in the ocean's a real nightmare. It barely spreads out, doesn't break down in seawater, and loves sticking to any surface it touches. For example, to sea ice. Or the opposite, it sinks and mixes with water, turning into a thick emulsion instead of calmly staying on the surface or evaporating like lighter types of oil. Plus, cold water only makes the situation worse. In the cold, this fuel evaporates slowly, so its traces stay visible much longer. It's like trying to wash cold grease off a plate. Nothing happens, it just smears around. I've got a couple of examples for you. On August 6, 2020, a Japanese cargo ship spilled fuel oil right into the crystal clear waters of Mauritius coral reefs. And yes, this wasn't just some small leak, it was a full-on environmental disaster. It all started on July 25th. The MV Wakashio strayed off course and for some reason came way too close to the shore. About a mile from land, it slammed into a coral reef. For almost 2 weeks, the hull creaked under heavy waves until it finally gave in. On August 6th, the fuel started leaking into the water. More than 1,000 tons of oil poured into the lagoon. Protected wetlands, a bird sanctuary, and habitats of rare animals were polluted. It was a blow to one of the most fragile ecosystems in the Indian Ocean. And that's when something incredible happened. Thousands of volunteers rushed to the shore to contain the spill. People stitched long improvised booms out of fabric, stuffed them with sugarcane leaves, cut their own hair, and added it inside because hair absorbs oil very well. They put empty bottles inside the booms so they would float. While some were collecting the fuel oil, conservation workers were pulling seabirds out of the sticky mess, carrying baby turtles to safety, and rescuing rare plants. And now the most absurd part. The Japanese operating company said the ship came so close to shore because the crew was trying to get mobile signal. Yes, a 1,000-ton fuel spill caused by an attempt to make a phone call. The investigation confirmed that human error was to blame. But then things got even worse. A representative of the International Maritime Organization said the leaked fuel was just like skin cream. That's, to put it mildly, not true. The ship was carrying VLSFO, a cheap blended fuel made from refinery leftovers mixed with cleaner products like gasoline or diesel. VLSFO has a lot in common with traditional heavy fuel oil. It's just as thick, just as gooey, and it hardens in water just as fast, turning into a sticky rock. Cleaning it up is almost impossible. Later, researchers directly stated that VLSFO spills stay on the surface for an especially long time, and dealing with such spills can be even harder than handling regular bunker fuel, especially in cold water. And here's another fresh example that shows just how bad things get when this kind of fuel spills. In December 2024, 2 tankers carrying petroleum products went down in the Kerch Strait. About 3,000 tons of fuel oil spilled into the sea. There were over 9,000 tons on board in total, meaning roughly a third of the cargo leaked out. Back then, the Ministry of Emergency Situations said the weather was to blame. Squally winds and waves reaching 7 on the scale. A tanker in conditions like that's almost like a bus sliding on ice, only way worse. Meanwhile, the fuel oil that spilled there is almost identical in its properties to the heavy fuel we're talking about today. It starts solidifying at just 77 degrees Fahrenheit. Plus, it doesn't just float on the surface like regular crude, it sinks down into the water column and even to the seabed. And that's where no one has any idea what to do. There are no technologies in the world that can collect fuel oil from the water column, none at all. All people could do was clean the beaches, gathering whatever the sea threw back onto the shore. Another issue revealed itself later. Sunken tankers resting at depth can still contain massive amounts of fuel, of course already solidified, which means you can't pump it out because you'd have to heat it up. And who's supposed to do that on the seafloor? Aquaman? So the conclusion's simple. You have to lift the entire tanker along with the frozen fuel oil inside. And even that doesn't guarantee safety because different types of fuel oil freeze at different temperatures. Sometimes it hardens completely and sometimes only forms a crust. And if there's still liquid under that crust, raising the vessel could cause another spill. So the debate around asphalt fuel is heating up. The risks of transporting heavy fuel oil are well known, and the G7 leaders have openly called it the biggest threat to the Arctic marine environment. In March 2016, Obama and Trudeau, in their joint statement on climate and energy, stressed that we urgently need to figure out how to deal with the risks linked to using heavy fuel in Arctic shipping and with black carbon emissions. Black carbon is soot that settles on snow and ice, speeds up their melting, and disrupts climate processes even more. Because of all this, transporting heavy fuel has become such a controversial topic that 2 different approaches to regulating it appeared at the same time. The first option's a straight-up ban. This idea was discussed for a long time in relation to the Arctic to completely remove heavy fuel transport by single-hull vessels. The Arctic is especially vulnerable with strong ultraviolet radiation, and in such conditions, fuel oil becomes even more toxic. The second option is the creation of special emission control zones. These are areas where ships are required to either use cleaner types of fuel or install exhaust cleaning systems known as scrubbers. In one of these zones around the English Channel, the allowed sulfur content in fuel was cut by 90%. But what's the whole deal with the Arctic anyway? Why does this fuel become such a huge threat specifically there? Let me try to explain it as simply as possible. According to the Polar Code of the International Maritime Organization, roughly 10% of ships in Arctic waters were running on heavy fuel. And activists have been sounding the alarm for more than 20 years. They've been trying to explain that this type of fuel could finish off the Arctic faster than anything else. The problem is that Arctic shipping keeps growing. Between 2021 and 2023, the number of unique vessels in the region went up by 37%. The ice is retreating, resource extraction is increasing, and every year more ships are showing up. Oil spills are dangerous anywhere, but in the Arctic, the consequences multiply tenfold. On July 1st, 2024, they even introduced a ban on using heavy diesel fuel here. It's especially dangerous in cold latitudes because burning it releases black carbon, soot. It's a double blow to the Arctic, and the atmosphere heats the air, and then it settles on snow and ice, making them melt faster. And that's just the tip of the iceberg, as ironic as it may sound. In cold water, heavy fuel doesn't break down, spread out, or evaporate. It just turns into solid lumps, sinks, and gets stuck in the seabed. Meaning it doesn't disappear, it just stays down there for years, damaging the environment. Add to that the specifics of the region. The Arctic is far from major ports. It has no proper infrastructure for dealing with accidents, and the sailing conditions are dangerous on their own. So any cleanup operation becomes a long, complicated, and often pointless process. Arctic animals suffer the most. Seabirds and marine mammals gather in huge groups during migration, breeding, feeding, resting, molting. One spill affects a lot of animals at once. On top of that, many species live long and reproduce very slowly, so it's incredibly hard for them to recover from losses. Of course, people are trying to do something about it. The use and transport of this kind of fuel in Antarctica has been banned since 2011. Environmental groups spent years pushing to extend this rule to northern waters, and in 2021, the member states of the International Maritime Organization finally agreed to a ban. Now the restrictions coming into force in Arctic waters. Activists welcome the progress, but they put it bluntly, there are too many loopholes and they could nearly wipe out the effect. For example, the ban doesn't apply to ships with so-called protected fuel tanks. That's when the tank is built so that in case of damage, the fuel doesn't spill into the sea right away. Sounds good, but in reality, it's just a way around the rule. On top of that, countries that control territorial waters in the Arctic can decide for themselves whether to apply the ban to their own ships or not, and that's a huge gap in the regulations. Take Russia, for instance. It's one of the major players in the region. It has more than 800 vessels operating in northern waters, and many of them still run on heavy fuel oil. They're not following the new rules. Activists bring up another example, Norway. The rules are strict there. The area around Svalbard already introduced a full ban on heavy fuel use, and importantly, it actually works. Recently, for example, an Irish vessel was caught breaking the rules and fined $93,000. So if a country really wants to keep things in order, the tools are there. But what about alternatives? Strangely enough, it's ammonia. In Copenhagen, inside a massive testing center, there's an engine the size of a 3-story building. It growls so loudly that the entire workshop shakes. Next to it, in a glass booth that looks like a ship's bridge, engineers listen to every sound it makes. Normally, an engine like this pushes giant cargo ships across the seas, but today, it has an unusual task. They're trying to make it run on liquid ammonia. Yes, that very same chemical most people associate with fertilizers and explosives. The shipping industry accounts for roughly 3% of global emissions, and some experts say that one way to cut those emissions is to switch to ammonia. In 2024, in one of Western Australia's largest ports, ammonia was transferred from one vessel to another for the first time. It became a sort of dress rehearsal for how this product could be used as fuel. The first cargo ships running on ammonia are promised for 2026, finally taking a shot at shrinking the carbon footprint. Ammonia is one option because there's also liquefied natural gas, methanol, biofuel. The list is pretty long. But here's the problem. Ammonia is an extremely controversial choice. Yes, it doesn't emit carbon when it burns, and if it's produced from hydrogen using green energy, then it basically becomes a zero-emission fuel. Looks fantastic in theory. But theory and reality, as usual, aren't the same thing, because ammonia is very toxic. It's a chemical that's tough to handle even on land, let alone on a ship in the middle of the ocean. It's poisonous when inhaled, it irritates the skin and eyes, and any leak can kill everything around it. Plus, there are no proper rules or standards for using it in the maritime world. Little practice, little experience, little infrastructure, and at the moment, no one is clearly accountable for safety. Shippers aren't rushing to switch to ammonia yet. As of 2024, only 25 vessels worldwide have been ordered that can run on a mix of ammonia and regular fuel. For comparison, there are already at least 722 LNG-powered ships and 62 methanol ones, counting both those already operating and those on order. There's also the economic factor. For ammonia to become a real alternative, its price would have to drop a lot. Industry estimates say that fueling a ship with ammonia is 2 to 4 times more expensive than with regular fuel. The reason's simple. Right now, the maritime sector barely uses it, and its energy density is about 2.5 times lower than that of traditional fuels, meaning you need more volume and more money. If you want to cover the same distance on ammonia, you'll either have to carry 2.5 times more fuel or refuel much more often. Plus, ammonia engines need extra maintenance. It causes corrosion, meaning it gradually eats away at metal. Even so, the American Bureau of Shipping predicts that by 2050, about a third of all marine fuel will be ammonia. But that brings a chain of problems right away. Ammonia is toxic, explosive, and it corrodes materials. Because of that, it needs special pipelines, special tanks, and special trucks. Everything has to be as sealed and corrosion-resistant as possible. Overall, ammonia doesn't have the infrastructure it needs, and without it, it won't help the planet at all. If anything, it'll just make things worse. You owe me a like. See you later.